Hello viewers, welcome back to this course. So today we will start with the lecture 11. So in the lecture 11 we will talk about the order of convergence, of an iterative method. So that is the, you can write down the order of convergence of an iterative method signifies the rate at which the, for example, nth iteration, maybe I represent by xn, approaches the exact root. So maybe I call it alpha as n increases. So that gives me that, because let alpha is the exact root and En represent the error alpha minus x n. So because this is the error En and alpha is the exact solution, and this is the approximation at the nth iteration, nth step. So that gives you the value of En. Similarly, I can define the error at the n minus 1th step. So that will be E x n minus 1. So from here I will define En is equal to some constant c E n minus 1 power p. So if I write like this one, then it shows that whatever the error was there in the n minus 1 step, I will take the power p, multiply by some constant, that will be the error at the nth step. So in this case the p is called rate or order of convergence, and c is a constant. So that we can find from the various method. So c is the constant and p is called the rate of convergence. For example, so in a method, suppose in method I get En is equal to some constant c En minus 1. It means whatever the value, the error value is there at the n minus 1 step, I will just multiply by c and I get the error here. This one I can write as c, and this En can be written as c E n minus 2. This one again I can add c into c e raised to power n minus 3 and so on. So in the end I can get value of, because n minus 2 it is giving the 2c, so I will write my nc, so it will give the value of E0. So it shows me that En, if the I have a order of convergence that is linear, means value of p is equal to 1 here. So from here I can write that E is equal to E0. So it gives me that whatever the error was there at the initial step, because initial step we have approximated the root. So whatever the initial approximation I have taken, so this is the error at the initial step, I will multiply by c raised to power n, that gives you the error at the nth step. Or you will see in that in some cases we get En is equal to some c En square. So in that case I will say that this here, this method is quadratic and the order of convergence is 2. So the more the order of convergence, the faster the method will be. So that is called the order of convergence. So now we start with the methods. So in the bisection method we have started. So in the bisection method you can see that at each step we are reducing the interval length by half. So the order of convergence of bisection method is 1, because at every time the interval length is reduced by half, so it means the error is reduced by half. So that is the bisection method. Now we define the another method, and that is called the famous one, fixed point iteration. Iterative method. So it will use the fixed point theorem. So for example, I have my function f(x) equal to 0. So this is my equation, and I want to find the root of this equation. So let alpha is the root, or maybe alpha is a root, because is a root, then f of alpha will be equal to 0. So in this case, what I will do is that we will reduce this equation into this form, so that I can write this equation as x is equal to sum phi x. So I will reduce this function into this form. For example, suppose I have a fx, like in the previous MATLAB code, we have started with cos x minus x e raised to power x. I think that was the function we have taken. So in this case, what I will do, I will write this function as I can write this function as cos x, so that is equal to 0, is equal to x e x. So from here I can write my x is equal to cos x divided by e x. So this one can be written as phi of x. So this equation I can reduce into this form, or maybe from here I can write x is equal to cos inverse x e raised to power x. So this is my phi x. So I can always write my function in this form. So this is my equation, and from this equation I have written like this one. So what is this? That in this case, now I have this equation. So just to find the root of this equation, I will apply the fixed point. So for example, this is my x axis and this is my y axis, or maybe phi x I can define, or I can define my y axis. So this is my y axis, function of. So this is my x axis. So suppose I let my function is phi x. So I draw this function phi x here. Okay. So this is my phi x. Now what I do, I draw the another function, that is, so now I have two functions, y is equal to x and y is equal to phi x. So this is my y axis. So this is my phi x, and then I will draw y is equal to x. So this is equal to y equal to x. So this is straight line, and now this is the point where it meets the x axis, that is called the fixed point. So at the fixed point, my x and y is same. So in this case, I will get my x is equal to y, and that y is my phi x. So basically this value of x where it meets the function phi x is the fixed point, and this is, if you see, so suppose this value is coming, maybe I will call it a. So from here you can see that my a will be phi a, and from here I can write my a minus phi a will be 0. And what is this? This is my value of the function at a. So from here I can say that this a is a root of the equation f(x) equal to 0. So based on this iterative method, the fixed point method, we are able to find the root of the given equation. So, based on this one, now how we can find this root using the iterative process. So, this fixed point iteration means that now I can write my equation. So, from the above, so this is my equation number 2. So, equation 2 can be written in an iterative process as x n plus 1 is equal to phi at x n, where n is starting from 0, 1, 2, 3 and so on. So, in this case what I will do? I will start with my f x 0. So, that is my initial approximation. So, x 0 is an initial approximation to the exact root, that is alpha. So, from here I will get my value of x 1. Now, I will do what I will do, I will find the put the value of x 1, I will get the value of x 2. So, that is my second approximation. I will use this x 2, I will get x 3. So, this is the third approximation. So, based on this one, I will iterate my or improve my iteration, improve my approximation value of the root, and after some time where I need to stop, I will find out that my value of a is approximately coming same as value of phi a. So, that is depend upon my tolerance, that how much tolerance I am giving. So, in this case what is happening, my value of a minus phi a, this is coming less than tolerance. So, once it reached, then I will stop this one, and from there I will say that a is an approximate root of the equation f x equal to 0, and based on this one I can find my error also. So, based on this one, from here you can see that I can find my error E 0, that is alpha minus x 0, E 1 alpha minus x 1, E 2 alpha minus x 2 and so on. So, E n will be alpha minus x n. So, whatever the error I am getting after the nth iteration, that will be E n. So, in this way we will see in from the computer programming that this error is reducing, and then ultimately after doing some iterations will reaching the required number of solution, that how much accuracy is needed in the solution, because in this in the iterative process we never get the exact solution. So, exact solution and always we will get the approximate solution. So, this approximation can be improved based on what is the value of the tolerance, because if from here if I give the value of the tolerance is half into 10 raised to power minus 4. So, it gives me the accuracy 0.00005. So, from here I can say that whatever the solution I want a and phi a, that should be same up to 4 digit and less than, so value should be less than this one. So, suppose my a is coming in some case, suppose my a is coming 0.51774. So, for my phi a is coming 0.51773. So, in this case my a minus phi a will be 0.00001 and it is less than the tolerance. So, it will stop. So, that is satisfied. So, this is okay. So, in this case I can say that my approximation is correct up to 4 digits. So, that is the way we can find the accuracy. Now, we want to find the that. So, I will start with the now this is my n plus 1 is equal to So, this is, suppose I take the iterative process. this is my iterative process, xn plus 1 is equal to phi of xn. Now, so this is my iterative process. Let alpha is the exact root. Now, I want to see what will happen. So, En plus 1 is the error, I can write alpha minus xn plus 1. So, from here I can write that xn plus 1 will be alpha minus En plus 1. So, equation 1 can be written as, so I will put this value of xn here in the terms of error. So, I will get alpha minus En plus 1 is equal to phi. So, xn I can write the same way, alpha minus En. Now, phi is the function that is continuous function as well as differentiable. So, I can apply the Taylor expansion for this one. So, I will apply the Taylor's expansion. So, Taylor expansion is that I will get phi of alpha minus En phi dash alpha plus En square by 2 factorial phi double dash alpha minus En cube by 3 factorial phi triple dash alpha and so on. So, in this case I know that my error En is small. So, En square, En cube and all other value will be even much smaller. So, based on this one I can ignore these values. So, from here we know that phi of alpha is equal to alpha, because this is the exact solution and in my iterative process phi of alpha will be equal to alpha. So, from here I can cancel out this one. So, based on this one I can write my En plus 1 is equal to, so minus En I can take common. So, based on this one I can write En phi dash alpha minus En square by 2 factorial phi double dash alpha and so on. So, based on the value of the En we ignore En square and all higher power of En. So, based on this one I ignore this value and all the values after that ignore. So, based on this I can write En plus 1 is equal to phi dash alpha En. So, that is my iterative process is there. Now, if you remember, then this is the way we have written the order of convergence. Now, in this case what is happening? Suppose I start with E0 and then I multiply by phi dash alpha and then I get E1. Now, I want that the error at the next step E1 and then phi dash alpha I will get E2. So, I want that my E2 should be much less than E1, then E3. So, this is only possible when the value of phi dash alpha is less than 1, because if it is greater than 1 the error will increase as we keep on doing the iterations. But if the value of f dash phi is less than 1, only then I can say that if I go for the more iterations the error will decrease as the iteration will grow on. So, in this case phi dash equal alpha is less than equal to 1. So, that is we call it the necessary and sufficient condition for convergence of an iterative method. Convergence of an iterative method, x is equal to phi x plus 1 n. So, that is my iterative method x n plus 1 is equal to phi x n. So, that should be that is the sufficient and necessary condition. It means that if I start with any, if I start with any iterative process, that is my x n plus 1 and that is equal to phi x n, then what I will do that I should first know the value of alpha, but this value of alpha is not available most of the time. So, in that case what we will do, because I know I will start with always x0, that is the initial approximation. So, to start with I want to start a iterative process. So, I will start with phi x0 and I will choose my phi in such that the value of this is less than 1, because in this case my initial approximation I can choose and my phi I will choose in such way that the value of this is less than 1, and then using this one I will start the iterative process. So, based on this one I can start my iterative process. Now, order of convergence. So, what about the order of convergence? So, just now we have seen that E n plus 1 is equal to phi dash alpha E n. So, I can choose my C is equal to phi dash alpha, okay. And based on this one, and this value is definitely will be less than 1. So, from here I can say that the C is less than 1. So, based on this one I can write that E n plus 1 is equal to C E n and P. So, P is equal to 1. So, from here I can say that the order of convergence for fixed point iteration is linear, and that is equal to 1 in this case. So, it is coming 1. So, the order of convergence for the iterative process fixed point iteration is 1. So, linear, I can say that these methods are linear in this case. Now, the question comes that how we can choose the phi. So, let us do an example. Let me take f x is equal to x cube minus 2x minus 8 equal to 0. So, this is the cubic I have and I want to find the root of this equation. Okay. So, what I will do is that now I want to solve this one, solve using fixed point iterations. So, fixed point iteration I can solve this with the bisection also, but I want to solve with the fixed point iteration. So, I need to convert this one into the form of x equal to phi x. Now, I can just for checking I will get f0 if I put, that is minus 8, f1 if you see this is 1 minus 2 minus 8 is equal to minus 9, then I will find out what is f2. So, it will be 8 minus 4 minus 8 is equal to minus 4, f3 27 into 6 minus 8. So, this is positive. So, from here I can say that my f of 2 into f of 3 is negative. So, root lie in 2 3. So, root lies here. Okay. Now, I want to find the roots using my iterative process. Now, what I do is that I can write from here like this one. So, this equation number 1 can be written as x is equal to x cube minus 8 by 2. So, this is the case 1. So, I can write this equation as x cube, this one I can take on the right hand side. So, x cube minus 8 and divide by 2. So, in this case my phi x will be x cube minus 8 by 2. Now, from here if I find what is my phi dash x, so it will be 3x square by 2, that is it. Now, from here if I see that if I put the 2 here, so phi dash at 2 will be 6, so greater than 1, phi 3 will be 927 by 2. Okay, so that is also greater than 1. So, in this case I cannot choose phi x. So, this phi x we cannot choose. I will take the case 2. So, in the case 2 what I will do is that I can choose my x is equal to maybe I will take 2x plus 8 on the right hand side and then take the power 1 by 3. So, in this case my phi x will be 2x plus 8 1 by 3. Okay. So, now my phi dash x will be what? So, it will be 1 by 3 2x plus 8 1 by 3 minus 1 into 2. So, that will be 2 by 3 2x plus 8 2 by 3. So, this will be my the phi dash x. So, now in this case I will just check that what will happen. Now, my phi dash 2 I will check. So, this will be 2 3, it will be 4 plus 8 12 2 by 3. My phi dash 3, so that will be 2 by 3, so 3 into 6 14 by 2 by 3. So, this value is less than 1 and this value is also less than 1. So, from here we say that we can choose this phi x. So, phi x I can choose here, that is 2x plus 8 1 by 3. So, based on this one if I do the calculation I can take this value of phi x. So, that is the phi x we are getting. So, based on this one I can take different value of phi. So, once I get this value of phi I will stuck to this one and then I will do this. So, in this lecture we have discussed about the fixed point iteration, and based on the fixed point iteration we have tried to find the necessary and sufficient condition, so that my iterative method should converge, and then we also showed that it has a linear convergence. So, in the next lecture we will continue from this one. So, thanks for watching, thanks very much.